these two components, f prime of t0 and g prime of t0. But then, of course, what is the slope? What is the tangent of this angle? Well, this is a triangle with a right angle, and so the tangent by definition is this side divided by this side, and lo and behold, you get back that formula. So what we get now, with more precise information about what the tangent vector is really consistent with the old information, which was just about the tangent of this vector, also known as slope. In a three-dimensional space, we can't really talk about the slope because now our vector has three components, so we can talk about ratios of different pairs of components. There is not a particular pair of components that is special. But in two dimensions, there are only two coordinates, and therefore we can talk about the ratio of the second one to the first one, which is what we call the slope. So thinking in terms of vectors kind of allows us to generalize the analysis we did for plane curves to the case of curves in free space. Okay, so that was my last comment on this subject. And now I want to talk about functions in 2 and 3 variables. So the next topic is functions in 2 and 3 variables. So in fact, I would like to put it in a more general context. Up to now, we have talked about different kinds of functions. We have talked about functions in one variable, which we usually write like this, f of x, like x squared or cosine of x or e to the x. This is a function in one variable. And today, we talked, and a little bit last time, we talked about vector value functions. Which we write as r of t. And these vector value functions may take values in vectors in two-dimensional space or in vectors in three-dimensional space. So in both of these cases, the word function is used, which begs the question as to whether these objects really are similar and in what way. What are functions? And this is really very elementary and very intuitive, but we have to say it once and for all, so that there's no ambiguity left. So the question is, what is a function? What do we mean by function in mathematics in general? Of course, in our everyday life, we use the word function. We say our appetite is a function of how much we've eaten before. So what does it suggest? It suggests a logical connection. If I ate a lot before, I'm not so hungry. If I haven't eaten all day, I was busy, then I'm hungry, right? So each cause has a certain result. So there's a certain rule, there's a certain logical connection, and that's exactly what we mean by function in mathematics. In mathematics, a function is a rule which takes each element of what we call the domain of the function, and transforms it to an element of what we call the range of the function. And the point is that we can choose as domain and range, we can choose all kinds of objects. And each time we make a choice, we get particular functions. For instance, to get a function in one variable, we choose as a domain R, the set of real numbers. And as a range, we also choose R, the same set of real numbers. Right? So it's kind of boring in a way, because we choose the simplest set in both cases. Not the simplest one, but perhaps one of the most obvious ones. So then the rule takes the following shape. Given an element of R, which we'll call x, so it could be any number, 0, 1, whatever, pi, this rule tells us what is the value of the function. So that's going to be another number, because, in general, it's going to be an element of the range, of the set, which we call the range. But range now is R again. So the result of the rule should be an element of. Right? So in other words, when we write the formula f of x, what do we mean by this? We mean that we have created a rule which assigns to any value x, we assign a certain value f of x. For example, say f of x is x squared. So that means that I can ask you, I can give you x, and you will tell me immediately what f of x is. Say x is 0, it's 0, x is 1, it's 1, if it's 2, it's 4. But it doesn't have to be an integer. Anything, pi, has a value for any value. I can substitute it into this function and get this. In other words, it is just writing this formula is just a very canonical way to describe this rule. Instead of making a table where for each value of x I will write the value of f of x, and actually I wouldn't be able to do it because there are infinitely many values. Instead of making this table, I just do it in a single formula, because this formula, I can use this formula to convert any given value in the domain into a value in the range by simply squaring it. Right? So one formula takes care of all elements of the domain, which is the set of real numbers. That's what I mean. That's what we mean when we say function f of x. It's not one number. It's not even a rule which assigns to one number another number. It's a rule which assigns to any number here, which is r, some number here. Okay, is that clear? All right. Now, sometimes when we write certain functions, sometimes the domain is not necessarily the entire R. For example, sometimes we write f of x is 1 over x. So in this case, we cannot say the domain is R, because the value x equals 0 is forbidden. This rule does not tell us what the value is at x equals 0, because at x equals 0, to get the rule from this formula, we would have to calculate 1 divided by 0. We know that 1 divided by 0 is meaningless. There is no such number, 1 divided by 0. So we have to make some adjustments. And the simplest adjustment is to say the domain for this function is not R, but is R without this point 0. So all non-zero numbers. Okay. So, but the function doesn't have to have as a domain R and a range to have R. A function could have any domain and any range. For instance, let's say the domain is the set of all students in this class. Okay. And the range is letters A, B, C, D, and F. Okay. So the function is a grade, the final grade. Okay. Because grade, well, it's actually more because it's like A minus, A plus, B plus. Okay, let's simplify. So A, B, C, D, and I don't know why there's E because it's never used. So let's say F. Anyway, we'll hope that we don't have so many values like this. So in principle, any function can happen, right? In principle, and I personally, I wish that everybody gets an A. So it's possible if everybody gets great results on tests and everything. Everybody will get an A. Now, historically, that's not what has happened. So I don't, realistically, I don't expect that. So this is a function is going to be, sometimes people call this a curve, because you can look at the scores and then you can try to draw the curve, looking at the number of people getting certain, and so on, right? So it's already suggests some connection to functions, but just think about it in a simple way. Each student gets a grade, so that's a function. Each element in the domain, which is a student, gets a grade, which is a letter from A, B, C, D, F, say. So that's a function too. We don't know yet what the function is. We will find out by the end of December. But this is also a good illustration, just by way of example, that anything where you have a certain input and then have a rule which transforms this input into some output is a function. Now, in this course, we look at domains and ranges, which are R to the n. So in other words, what we're going to do now, and what's different between this course and the previous calculus course, which had to do with single variable calculus, is that we are going to allow not just R going to R, but we will look at R to the n, going to R to the m, where n and m take values 1, 2, and 3. You have a question? Say again? Oh, this one. Okay, the question is about this notation. Is this notation familiar? No? Okay, so I'm glad that you asked me about this. So this means belongs to. This means belongs to. Or is an element of the set. And this means the same, but now in this direction. So I just switched it. Usually we write like this. I did this to make it look nicer. Because then I have to, otherwise if I switch them, I have to draw a curve like this. But it's the same. The three ends is to where it belongs. So this means x belongs to R to the n and not the other way around. And here f of x belongs to the R to the n. It's clear now? Okay, good. So the domain range that we're going to look at in this class are usually going to be R to the n and R to the m, which means R, R2, R3. Okay? Sometimes we'll have to look at some subset here. We'll have to remove something because function, for example, may not be well defined at a certain point. Like this function. This function 1 over x is not well defined when x is equal to 0. Or more precisely, this rule does not tell us what to do at x equals 0. So that means this rule is really only defined for the domain R without the point 0. Something like this can happen here as well. Okay? And so now, if we stand on this point of view, that there are these functions which have as domain R to the n and as range R to the m for some n and m, 1 to 3, which could be arbitrary, not necessarily equal, then we can describe all the previous examples as sort of object under the same umbrella. Because, for instance, vector value functions we can now interpret as functions in which the domain is R. Domain is R. And that's where our variable t is going to live. And the range is R2 or R3. So in other words, in the case of R2, you will have t going to f of g and g of t, an element of R. See, you can also do the sign in this way. And then you get an element in R2. And likewise, in R3, each t will go to f of t, g of t, and h of t, which is in R3. So again, a point in R will go to a point in R3. Note that there is a small difference, which I already mentioned earlier, which is that you can treat f of t and g of t as components of a point or as components of a vector. So now I'm really standing on the point of view that I'm getting a point in R2 instead of a vector. But because these are so closely related, we can think about both scenarios as functions. It just becomes really a matter of what do I mean by R2 or R3. Do I interpret R2 as a set of points or as a set of vectors? And in fact, it's better to think of it as a set of vectors, but we oftentimes think of it as a set of points. But the points and vectors are given by the same information, by two components anyway. So that's why I'm really thinking of R2 as being collections of two numbers, x, y, first coordinate, second coordinate. You see? And so I'm not worrying about the fact whether these are components of a point or components of a vector. I know that in each particular situation, in any given context, I will be able to interpret it in the right way. I'm just using the fact that it has two components. Okay? So vector value function now becomes an example of a function because it's just a rule assigning now to a single variable, to a single number, which we usually call t, a pair of numbers like here or a triple of numbers like here. Does that make sense? Yeah? Okay, so that's what we mean by function with values in vectors. So in this case, our domain is R, is always R, but the range is R3 or R2. You see? So we go sort of from the smallest one to the two big ones, R2 and R3. And now we can understand very easily what are functions in 2 and 3 variables. It's sort of the opposite situation, where the domain is R2 or R3, but the range is R. So in that sense, it's no more difficult to understand as a concept than vector value functions, or even just ordinary functions from R to R. It's all part of the same story, of the same concept of functions. So going back to the title of this topic, functions in 2 and 3 variables, by function in 2 and 3 variables, I simply mean a rule in which the domain is R2 or R3. If I want 2 variables, it will be R2. If I want 3 variables, it will be R3, and the range is R. So maybe I will write it here. Let's just write like this, R2 to R, and R3 to R. So then how to express such a rule? So domain is now, say, R2. So it's a set of all pairs of points. And the range is just R. So it means that each xy has to go to some number. So we have to denote this number in some way. And the way we denote is say f of xy. Okay? For example, I can write f of xy is equal to x squared plus y squared. What do I mean by this? I mean that whenever you give me some values xy, I can substitute them into this formula, and I get a number. You give me two numbers, but I give you one number because I do something with them. I take a squared and y squared, and I take the sum, so I get one number. So it is a rule which assigns to this one number. That is an element of R. That's why writing this formula can be interpreted as giving a function in two variables. Two variables because I pointed R2 has two components, x and y, which you think of as two variables. So again, I could try to make a table, different values of xy and corresponding values of f. So for example, I start with 0, 0, I get 0, I start with 1, 0, I get 1, I start with 1, 1, I get 2. But of course, I cannot make the table for the entire R2 because there are infinitely many points in that table. So instead, I simply write this formula. So this kind of functions appear in real life all the time. And a typical example could be a map of temperatures or atmospheric pressure. In this case, you can think of some domain being you can draw a map of a certain region, say the Bay Area, and then you plot it on the SY plane so that each point in the Bay Area gets coordinates x and y. And then you say, like on television, when you watch the news, they show you this and they write in on temperature, like 85 degrees or whatever. Here, and then maybe here it's like 90, and then here they say something else, 83, and San Francisco will be like 55. No, I'm joking, maybe on a day like this, maybe 70. Okay, so what is it? You assign a value to each point. So you are defining a function. Each point on this map, each point in this region, x, y, corresponds to a certain temperature. So to each point you assign a temperature. So that's an example of a function. Likewise, you can think of the landscape. You can think of the map of this area, and you can look at the height of like each point, the height of this point as compared to the sea level. So then again, you get the height. The height gives you a function for each point x, y. You get the particular height, and this actually gives a way to leads to a nice idea of trying to interpret functions or visualize functions into variables in terms of graphs. Of course, for functions in one variable, this is a very old idea. Functions for one variable, we've been drawing graphs, for a long time, and this is almost a reflex. If I say y equals f of x, say x squared, let's just say f of x equals x squared. Okay, so you immediately think about this picture. So this is a picture which you draw on the plane by introducing an additional variable. So this is your x, and there's an additional variable you introduce to accommodate the value of the function. And then for each value, you plot the point on this plane by taking as the x coordinate the value of x, and as the y coordinate you take f of x. Of course, here again, there is a clash of notation, which you have to realize. I mean, it's sort of again very clear from context, but I would like to mention it anyway. When we talk about functions in one variable, we talk about the graphs, and the graph of a function in one variable lives on the plane. So even though in your original problem, the domain is one-dimensional, it's just x. There's only one variable. You are forced to introduce a second variable, just because you also want to accommodate the value, the range, the element in the range. And we usually call this coordinate y. So we write the graph as y equals f of xy. Y is equal to f of x. But this y has nothing to do with this y. Because when I talk about functions in two variables, I talk about functions in x and y. Why? Because x and y is like the two variables, they go next to each other in alphabet. So it's natural. Once I say x, I have to say y. You'd be surprised if I say a function of x and a or something. It's like, what's wrong with him? Why is he talking about? Why is he talking like this? So once I say x, the next one is you say y. But now, in this context, y has nothing to do with the domain. This is the domain. It only has one variable. And this y corresponds to the range. You see? But now, when we talk about functions in two variables, we use the same notation, x and y, to indicate the two variables in the domain. So now, to draw a graph of this function, we have to go to the three-dimensional space because we have to introduce one more variable which corresponds to the range. The range in both cases is r. But here I denote it by y because I use just x, and so the next letter that comes is y. Now I already use x and y for my domain. So I have to use a different coordinate, different name for the range, and usually I say z just because it's the next letter in the alphabet. Right? So, for instance, if I choose as my function in two variables this function f of xy equals x squared plus y squared, what kind of picture do I get? It will just be a surface given by the equation z equals x squared plus y squared. And fortunately, we have already discussed this surface, so we know what it looks like. Right? This is an example of an elliptic paraboloid, which looks like this. Right? And I kind of want to indicate some more curves on it, just to give it sort of more shape. Okay? So that's a paraboloid. So this is the graph of the function, which is a paraboloid, elliptic. Right? Likewise, you can also talk about functions in three variables. So here I talk about function in two variables, but I can also talk about function in three variables. So in this case, domain is R3, and the range is R. R3, and the range is R. X, Y, Z, right? So, of course, this is also meaningful because, for example, if you talk about barometric pressure, you talk about atmospheric pressure, well, for temperatures, we usually just measure temperature at the surface, but for pressure, it makes sense to also look higher. So we're really talking about a point in space, and we assign to a point in space the pressure. So it's really a function in three variables. So really for each point in this classroom, there is a particular value. Temperature is also, for example, we could measure temperature, at each point in this classroom, and there will be some small variations. If you